This podcast is brought to you by LMU Munich.
Okay, thank you. I'm not sure what precisely your background is, so I'm going to start this lecture. Please ask questions, slow me down or speed me up. In my experience, nobody ever asked the lecturer to speed up, but I'll say it anyway. You can tell me afterwards if I'm going too slowly or too fast. Also, if there are some particular topics you really would like to hear about, you can ask me privately and I can adjust the next lectures to go in those directions. Okay. Okay, so today we'll discuss some aspects of entanglement and entropy in quantum field theory and gravity. And the motivation for doing this is, my particular motivation is to understand better black holes. But actually the same techniques are also useful for understanding better quantum field theory, the structure of relativistic quantum field theory. For example, and as an example of those applications, I could give some recent proofs of the C and F theorems, which are quantities which decrease under renormalization group flow, which are defined based on entanglement entropy ideas. And proven based on entanglement entropy ideas. And I might or might not talk about that depending on your interest. And so that's an example of a conformal of a quantum field theory application of these techniques. Of course, entanglement is an interesting property of quantum mechanics, and we'd like to understand it better. And we'd like to understand how the entanglement works in relativistic quantum field theories, in the vacuum of relativistic quantum field theories. Because in those theories, entanglement is very large locally, it's a divergent quantity, and we'd like to understand this better. So those are field theory applications. And also, from the gravity point of view, it seems to play an important role in the black hole, perhaps in the interior, that we think it plays an important role. Whenever we talk about entropy or entanglement entropy, people often say, well, look, entanglement entropy is not quite unobservable, because observables in quantum mechanics are given by trace of rho times O, where O is an observable, and so all observables in quantum mechanics are linear in the density matrix. So any experiment we design to measure an observable is something that is some operator O, and then we take its expectation value, we measure something which is linear in the density matrix. While entanglement entropy is actually nonlinear. And so it's difficult to design an experiment which actually measures directly the entanglement entropy for a given density matrix, or the entropy of just a density matrix, no matter how you define it. And well, that's true. Of course, in thermal or near equilibrium configurations, we can measure it by going from zero temperature and then increasing the temperature slowly and so on. That's how we measure entropy in thermodynamic systems. But generically, it is difficult to do this. Okay, so that's some reason why you would not want to study this concept of entanglement entropy. However, as I've mentioned, it's a very useful concept, and we'll often talk about it, entanglement entropy. And also, if you don't like just the entropy, we can certainly talk about the density matrix, and it will be important for us to understand properties of the density matrix itself. Okay. So the first topic will be Rindler space. So we take just ordinary Minkowski space, and we take two of the coordinates, x plus and x minus. So these are the two Lycon coordinates. You could think of this space as two-dimensional or as higher dimensional, with the extra dimensions going perpendicular to the blackboard. So we can write the metric of this space in the usual Lycon form. Or we can also choose coordinates where the metric has the form d tau squared plus, well, let me call this t, plus dr squared. And these are the so-called Rindler coordinates. The advantage of these coordinates is that they make the boost symmetry of the spacetime around the origin manifest. So the boost in the x plus minus plane, they make it manifest because the boost corresponds to change in x plus and x minus to e to the plus minus t x plus minus. So this is the usual definition of boosts. And so a boost, a boost by, let's say, some quantity alpha would change the coordinates in this way. And in this coordinate system, this just corresponds to t going to t plus alpha. Okay? So it's just a time translation of the Rindler time corresponds to a boost in the original coordinates. Okay? So if we take a trajectory or a line of constant r, so we fix r, and then we move in the time direction, we'll get lines which have this geometry of a hyperboloid. So those are the lines constant r. They have this shape. These coordinates cover only this right region. So the right region, or sometimes called Rindler wedge. Rindler. Okay. Now, an important result in quantum field theory, in relativistic quantum field theory, is the fact that this, if you are an observer who's sitting at constant r, and you conduct experiments, you will find that the vacuum, the standard vacuum of the quantum field theory, will look to you like a thermal state. A thermal state that has a temperature T, which is 1 over 2 pi r. Okay? So if you're sitting at some distance r, for you, the vacuum will have a constant temperature, which is 1 over 2 pi r. This is the proper temperature that an observer would measure. And this is sometimes, also people sometimes say that the temperature is, So in a situation like this, you see different observers see different proper temperatures. An observer who following this trajectory which is closer to the origin, it actually would see a higher temperature, as given by that formula. I'll give a derivation of this effect in a second, but I assume that most of you must have already know this, but I'll review the derivation later. But first, I would like to make some comments. First of all, notice that the temperature that observers at fixed r see gets increasingly high as you move closer to the origin. We sometimes, so question number one, so how can it be that, so if different observers are seeing different temperatures, does it mean that we're out of thermal equilibrium? In thermal equilibrium, shouldn't we all see the same temperature? Let's see, suppose we have a thermometer at the bottom of the room, and we have exactly the same thermometer at the top of the room. Do they see the same temperature, or do they see different temperatures? This room. We are in thermal equilibrium. They are not inertial observers. They are not. They are accelerated. And question, will they see the same temperature or different temperature? So some both the same, some both different, or they're all both the same, I guess. Everyone thinks it's the same temperature. Okay, so the correct answer is that they see different temperatures. And the reason is that that when you are in thermal equilibrium in the presence of a gravitational potential, so in a metric where G00 is not constant, the proper temperature actually in thermal equilibrium changes. And the reason is more or less, so let's first give the reason for the case of the air in this room. So we have the molecules here moving, but if they have to go to the top of the room, they lose some, they have to climb up the gravitational potential, and so they will lose some energy. So they will be moving more slowly. Right? So the thermometer here will see these guys moving more slowly. Okay, so that's that. And this is called the Tolman effect. It's important for stars and so on. So if a star is in thermal equilibrium, what's constant is not the proper temperature, but the so-called, perhaps you could call it the killing temperature. So it's the temperature measured with respect to the killing time, so or the symmetry. So we are imagining if we have a situation in equilibrium, we'll have a time-independent metric. And that time-independent metric will have a time-like killing vector, as, for example, we have in this case. Or more generically, we will have where this depends on R, but not on T. And so the temperature that is constant is when we measure energies relative to this time, right? So if we write the, let's say, partition function of thermal distribution in terms of energies measured with respect to that time, then we have a constant temperature. So the temperature defined this way will be the constant temperature. Okay? But the proper temperature, which is defined with respect to proper time, will not be constant. Right? So if this is dT proper, and if we were here to replace E proper by T proper, we will find the temperature proper, which actually depends on R. Okay? Okay, so that's as we normally have in a gravitational field, and we can view Rindler space as a space with a non-trivial gravitational potential. So here we have a gravitational potential which depends on R. G00 is the gravitational potential. It varies very rapidly with R. Right? So we go out in this direction, we see something colder. We go in this direction, we see something hotter. Okay? Okay, so that's one point. Now, as an exercise, you can take, exercise. Consider the four-dimensional case and take the free field in 4 dimensions, which has the usual 2-point function in Minkowski space, which is 1 over proper distance squared in Minkowski space. So this is a proper distance between 2 points, 1 and 2. Okay. And then take that same expression and express it in Rindler time for an observer who sits at the constant R. So put the values of R corresponding to one of these trajectories and put the values of time and see whether it has a thermal nature from that point of view. How would you recognize thermal nature? Well, one way to see that is whether one simple criterion is to see whether it's periodic in imaginary time. Okay? Because if you change that time to I, so you add I beta to that answer, it should be periodic, as it is for correlators in thermal equilibrium. Okay. Now, before we discuss a bit more even the derivation of this, let's discuss one further aspect, which we can discuss. Now, something important here about this effect is that the characteristic wavelengths, thermal wavelengths associated to this effect, are comparable to the distance to the horizon. Okay. So, if instead of having the full Minkowski space, we had, for example, a mirror set at this position, and then we ask, well, what would this guy here see? Will he see a thermal state or a non-thermal state? Well, in that case, the answer could depend on what could depend. He doesn't necessarily see a thermal state. He could see actually a state at any temperature, would be consistent. And that's not in contradiction with this idea of the Unruh effect, because the Unruh effect, or this thermal effect, is due to the presence of this horizon and the regularity of the fields at the horizon, on the horizon. If you don't have the horizon, you are not required to be at this particular temperature. Okay. Now, just to explain this a little better, let me write this temperature again, 1 over 2 pi r. Now, 1 over r is the same as the proper acceleration of that trajectory. So we could also write it as 1 over 2 pi times the acceleration. So one simple exercise that, so this is the acceleration of this trajectory, okay? So the guys that are sitting here are more accelerated. So they're more accelerated, they also happen to see a higher temperature. One simple exercise is to put in the h bars and c in this formula, right? So this is a formula with h bar and c both set to 1. And at least when I did this exercise, I got this. Maybe get something different. So first of all, it's important it's a quantum effect, so it has an h bar. When h bar goes to 0, this effect disappears. And another important property is that it is a relativistic effect. So if you send the speed of light to infinity, it also disappears. Okay? So this is an effect that puts together quantum mechanics and special relativity. And in fact, it's a very generic feature of relativistic field theory. So if they ask you, someone wakes you up at night and tells you, what is a generic feature of relativistic quantum field theory? One standard answer to that is to say the presence of antiparticles, for example. But well, if you don't have charged particles, you could have all particles be on their own antiparticles, so then that's meaningless. But you could tell them this Unruh effect is one generic prediction. And I think this effect is playing an increasingly important role in many of the current developments, and that's why I'm discussing it in some detail. So I'm assuming you have already heard the statement that it happens, and we are just discussing some of these details. One other important feature, well, one feature that I briefly mentioned before, but I'll repeat it again just to make it more clear, is the fact that this effect is actually a non-local effect. So you might be misled by this formula, because you might say, well, the temperature will be proportional to the acceleration, and so if I'm accelerating, I will always measure this temperature. So you sit in the plane accelerates, okay, my temperature goes up. I sit here on Earth, I'm accelerating, we are accelerating, right, g, 10 meters per second squared. We'll see a temperature associated, given by this formula. Now, this is the wrong conclusion, right? Now, why? So let's be more clear. Imagine that we are on the surface of the Earth, of a very cold Earth. Okay, so here we are. We have this acceleration g, 10 meters over second squared. Now, it's useful to also write it in units where c is 1. So this acceleration, so you can write it in those units, so you should have units of 1 over length or 1 over time, right? So in terms of length, this acceleration is 1 light year. Okay, you exercise, do this calculation. Hopefully you'll get the same answer. If not, you'll correct me. So it's a very, very long. So now this is a feature. So I'm just converting ordinary units for acceleration to length units. Now, why am I giving this unit? Why am I saying this? The reason I am saying this is because this is supposed to be the wavelength of the radiation we would see, right? So the thermal wavelength associated to the temperature given by this formula is 1 light year. Okay? Okay, good. Now, imagine we are here on the surface of the Earth, and of course, we are at the temperature which is much, much higher. I mean, the wavelengths associated to 300 Kelvin are, of course, much shorter than this. But imagine the Earth cools down to absolute 0, and we are sitting on that Earth at 0 naively at 0 temperature. Well, we let it cool as cold as it can be. The question is, can it go all the way to 0 Kelvin, or does it have to stop at this at the temperature given by G over 2 pi? So if you're naive and you say, I'm going to apply the equivalence principle, and I'm going to say, well, I'm accelerating. I don't care whether my acceleration is due to this gravitational field of the Earth or we are in Rinder space. So the local geometry around my trajectory. So local geometry, suppose I'm sitting here on the Earth at a distance of 1 over g, so 1 light year in Minkowski space. In Rinder space, 1 light year. The local metric around this region is exactly equal to the local metric that observer sitting at the surface of the Earth will see. Both will have the same. Both will feel the same acceleration. So do they feel the same temperature? So how many think the temperature will be given by this formula? So how many think that the temperature could go all the way to 0? It's not. You're not allowed to abstain. Okay. Well, the correct answer is that the temperature is allowed to go all the way to 0. So this guy could be at any temperature, including t equal to 0. So he could be at t equal to 0, and that's perfectly fine. And the reason is that this effect is non-local. So this effect, even though written this way, depends on the acceleration. It really depends on the whole geometry of Minkowski space all the way to the horizon. So in order for the derivation that we're going to give one derivation, but in order for the derivation of this effect to be correct, what we really need is to be able to trust the geometry all the way to the horizon, right? If we only know that we have a geometry which is similar to Rinder space in this little region, that's not enough for deriving this effect. And the reason is that these wavelengths are very long, and they can feel whether there is a horizon or not here. That's a hand-waving explanation for why this is the case. Perhaps a more correct explanation is that if we put, for example, a mirror here, right, so that we don't have this region behind the horizon, then this time translation symmetry becomes a globally well-defined time-like Killing vector, and we can use it to define positive and negative frequencies in our field, and we can use it to choose a vacuum, and that vacuum then will be at 0 temperature. So that minimum energy state will be at 0 temperature. On the other hand, if we don't have the mirror, then this translation symmetry, which looks like a time translation symmetry in this region, is actually not time-like in these regions where it's space-like, and even worse here, it goes backwards in time. So this is not a globally defined time-like Killing vector. Okay? And we cannot use it to define positive and negative frequencies for the quantization of fields, and so we cannot use it to define a notion of energy that is globally well-defined and a global notion of state. So that is, and as soon as we have a region near the horizon, okay, either here, or region here, and so on, where we cross the horizon, then we'll run into this issue, and under those conditions, we are forced to have this temperature. So we're forced to have the temperature if we insist in having regularity across the horizon. Okay? If we insist that the quantum fields are regular across this horizon. I'm calling it a horizon because for an observer who sits always in the positive Rinder region, this observer cannot receive a signal from the region behind this line. Okay? That's why I'm calling it a horizon. Okay. So what are the important point I was trying to make during the last 10 minutes is that this effect is non-local. So it's not, you need to be able to trust the geometry for distances which are big, or which are larger than the inverse temperature. Okay, so for distances which are comparable to the thermal wavelength of the associated temperature. Okay. So let's go back to the Earth case. So 1 light year is the thermal wavelength, right? Can we approximate the geometry that this guy sees all the way up to 1 light year and say that it's similar to that of Rinder space? Well, let's just do something easy. So here, the direction in which this field points, these gradient points, right, is this, well, would be analogous in this Rinder space as this radial direction, right? But somehow something different happens when he gets to the center of the Earth, certainly to the center, but even before, the properties of the acceleration are going to be different. And there, at the center, the acceleration went to 0. While here, if we move along this direction, the acceleration is going to get higher, right? So clearly, we cannot trust, it's not the same metric, right? It looks locally the same, but it's not the same for the distances. We want it to be the same in order to trust the derivation of the effect. I'm not sure if I'm making myself clear. Probably not. Your face is, I see some confusion. But
yes, I have a confusion
go
about
ahead.
basic Rindler wedge.
Yeah.
Sorry.
Mm-hmm.
So if I'm on this world line of constant
Yeah.
acceleration, I mean, I don't understand how I can see some temperature because it depends on what I will do in the future. Because if, as you say, it's a global effect. So if I stop accelerating, the horizon is destroyed,
Right,
and then all this computation breaks down.
Right, good,
But how,
good,
how can this
good.
how can measurement at some point depend on what I will do in
Good,
the future?
good, perfect. That is a good question. So your question is, in order to measure, so first let's do something like this. In order to measure some temperature along this direction, how long do you think you need to spend measuring this temperature?
Infinite time, I would say.
Well, but you know, you measure temperatures in the lab, you don't take infinite time.
No, right, but for this, yeah, okay, I don't know. So
Just physically, you need to take some time to measure a temperature, just to trust this temperature measurement. And it should be a time which is of the order of the inverse temperature, right?
yes.
So in units where C is an H bar 1. So that's the time for which you need to do the measurement, and that time we saw it's comparable to R, right? So you need to, this should last the time which is comparable to this. So you need a square roughly this region, right? Similar criterion to what we were discussing before. So if you start like this and then you move like this for a while, which is longer than this distance, right? Then you will see the temperature. You will see approximately this temperature, it's not exactly this temperature, but you'll see this temperature.
Okay.
Now, you can ask, how would you see this temperature? So first, in order to get more convinced about this, you could say, well, I'm going to make a model thermometer. And so my model thermometer would be that I would carry a 2-level system along the geodesic. So it could be like 2 particles of slightly different mass and so on. And I'm going to let that 2-level system interact with this field, with the field that is defined everywhere in space-time. And then see what happens with this 2-level system. I start in the vacuum, the lowest energy configuration. And then I let it interact and see what happens, whether it gets a thermal distribution or not. And so people have done this computation, and you can do this computation, and find that if this time is long enough, you will get something which is close to the thermal distribution. It won't be exactly the thermal distribution, as you said. You would need infinite time for that, but it will be close enough if this time is long. If you come here and you just follow this for a very short time, then that will not do it. Okay. Maybe I should have drawn this more. This way it's a little more physical. So if you accelerate only for a while, if the while is longer than the inverse temperature, then you'll see it.
But then although there is no horizon?
Yeah, even though there is, so in that case there is no horizon, but you still see this temperature. Yeah. You see it for a while. I mean, after you start moving with constant velocity, this temperature goes away.
Okay.
Any other question? Okay, so now I've been promising derivation of this, and the derivation I'll give is actually pretty close to the original derivation, which was actually given by Bisoniano and Wichmann before Unruh, but apparently people the effect didn't sink in. So they discovered this effect, but it's called Unruh effect. Because either they didn't explain it clearly enough, or they didn't understand that this is what it really meant. But I don't know about that one. I don't really know the history, but certainly their paper is before the Unruh paper and before Hawking. Yeah. Okay, so the discussion I'm going to make now is valid actually in general, for general field theory. And we are not going to derive directly the temperature, we're going to derive the density matrix. So what we're going to do is we're going to imagine that we're going to look at the following problem. Imagine that we have a quantum field theory which is defined on all of Minkowski space, but we make observations only in the right part of the space. Okay? For example, an observer who is following these trajectories and is doing observations here on this right half will only do measurements on this right half and will not be able to have access to the results of any measurements that are done on the left side. Okay? Is that intuitively clear? Yeah. Okay, so all those measurements can so imagine, just for the sake of the argument, that we have a scalar field, or we could have a general field theory. So in principle, the full state of the system at t equal to 0 is a wave functional, which depends on a function of x, okay, where x is this coordinate. So phi of x is the argument of the wave function, right? We're in field theory, so the wave function has an infinite number of arguments, okay? So that's the argument of the wave function. And we're going to divide these arguments into the phis that are here on the right and the functions here on the left, right? So we have some function on the right side and then also some function on the left side. So that will be our wave function. But all the operators whose expectation value we're going to calculate depend only on the phi here on the right, but not on the phi on the left. Okay. So we're going to insert complicated operators here. And therefore, the results of those measurements will depend on a matrix, will depend on a density matrix, which depends on two functions on the right, phi of x, and a second function, phi, let's say tilde right of x prime. I'm emphasizing these are two full functions that are defined on the right. So let me draw this way. So we have here two functions, phi of x and phi tilde of x, right? And maybe I should write bigger. Can you see this? Phi. I can see it, but probably from the back. Okay, so we have these two functions, which are the variables of the wave function here defined on the right. And we're going to construct the density matrix, which is equal, so this rho is equal to, as usual, we will trace over the functions left, which we're not going to observe, and then we have the phi, which depends on right and left, and the phi conjugate, which depends on phi right tilde and phi left. So here we have the same index. This is the same function. That's what we are summing over, right? And we're getting a density matrix. This is the usual. Well, maybe I should perhaps review the usual story for how we. I think my phone is doing that. No. So the usual story of when we have a wave function which depends on, well, we took two indices, alpha and beta, and we trace over, so define on a Hilbert space h left times h right, where the alpha index labels states here, and the beta index labels states here. Then, in order to define the density matrix, which depends on the on beta, beta prime, right? So we just define some, so we are just taking the trace over the H left Hilbert space of psi, okay? And that translates into this particular sum, right? So that general definition is the same as this. Is that crystal clear to everyone, or? Yeah? So we're trying to define this density matrix. And we're trying to define it for the vacuum. Okay. Now, one way to prepare the vacuum state in quantum field theory is to do evolution in Euclidean time. So we do evolution in Euclidean time, and we prepare the vacuum. So when we're talking about this vacuum wave function, so we have, let's say, the right side here, phi right. So we fix some boundary conditions phi right, and some boundary conditions given by phi left. And then we evolve in Euclidean time. We get some answer which depends on these two functions. And that is going to be equal to the vacuum wave function. Right? This computation of doing the path integral from Euclidean time from -infinity to 0 with these boundary conditions gives us the wave functional of the fields. Right? Is that clear?
So what is the boundary condition in the remote path?
Yeah, in the remote path, the boundary condition is that things are regular. So we just do the path integral. I mean, you could put some boundary here where phi, let's say, is 0, or phi is 1, or whatever you want, but regular, not phi equal to infinity. And if you do that, then when you take the limit that this boundary goes to infinity, the boundary conditions will drop out, and you'll get a unique answer, which is the vacuum wave function. All that I'm saying here is that we are doing Euclidean, so from some initial state, some random initial state, we are doing Euclidean evolution over a very long Euclidean time. This, if you take the limit when t goes to infinity, t going to infinity, limited, t going to infinity of this, projects onto the vacuum state, right? This is what is usually done when we prepare the vacuum in quantum field theory. You can view the Feynman's I epsilon prescription, for example, as a way to prepare the vacuum in this way. Okay, very good. So that's how we prepare the vacuum. Now that will give us this wave function. This is one of the factors here. And now we also construct the other factor, and we'll consider the other factor as doing exactly the same thing, but let's say from positive Euclidean times. This is again Euclidean time. From positive Euclidean time, we do exactly the same. I mean, the computation is essentially identical. The only difference is that here we're going to put the same boundary conditions, phi left and phi left, the same field on the bottom and the top. But here we put phi right on the bottom and phi tilde right on the top. Okay? So we put different boundary conditions on the top and bottom, just simply because that's what we want to evaluate. And then we integrate over all possible boundary conditions here, right? So integrating over all possible boundary conditions here is like removing this boundary. So that is exactly equal to removing this boundary here. And so now we have only one boundary. I separated these two, but they are both at t equal to 0. Okay, they are overlapping. So we are doing the path integral of the full quantum field theory on a space without the real axis and with these boundary conditions on the real axis, okay, on the positive part of the real axis. That gives us this density matrix that depends on the right and phi tilde. Okay, so this sounds a little abstract, but now comes the real simple thing, which is the fact that we can view this same calculation as evolving in Euclidean time by 2 pi. So we evolve in the angular direction by 2 pi. So we start from some initial condition, and then we evolve by 2 pi, and we get to this final state. So the point is, and this is the final, the important point, is that the density matrix is the same as evolving in Euclidean time times this rotation, so 2 pi times the rotation generator. Okay. That's this whole discussion was to derive this formula for the density matrix, which, going back to Lorentzian signature, we can be written as e to the minus 2 pi times the boost generator. Okay. Okay. So now what have we done? So we've shown that, and recall that this boost generator is nothing else than the Rindler energy generator. So it's in the Rindler coordinates, which are still written here. So that energy is the same as the energy that shifts time. It's this generator. So this is E Rindler. The action of E Rindler is to shift time in this way. Okay, to shift Rindler time in this way, and it's the same as boost in the original variables. And so we get this very simple formula for the density matrix. Okay. So we got this explicit formula for the density matrix, which has the thermal form with the temperature T Rindler, which is 1 over 2 pi, which is the formula that we stated here, and I promised to you that we would see the derivation, and this was the derivation. Okay. Now, this derivation looks perhaps different from, I think Rami Brunstein gave you a derivation of the Hawking effect, and perhaps also of the Unruh effect, which is essentially the same thing, using modes and Bogoliubov transformations and so on, and that's a perfectly fine way to derive it also. But this is a derivation that is a little more abstract and is valid for any quantum field theory, interacting or not. So here we have to be a little more abstract in the description of the boundary conditions, but in principle we consider arbitrary boundary conditions, and we sum over all boundary conditions, and that should work for any arbitrary quantum field theory. And so it shows the general feature of this thermal, the thermal nature of fields in the vacuum. And this formula again was derived by Bisoniano and Wichmann using slightly different arguments. These arguments were developed later, I think by Callan and Wilczek, though I'm not sure. And so on. Okay. Now, we can write down an explicit form of this boost generator in terms of the stress tensor. In order to do that, we need to, we write down, we can choose any spatial surface, either this or that, or any space-like surface. And there, on that space-like surface, write the expression for the boost generator, which is some integral of some component of the stress tensor. Okay. So it's a stress tensor in general. If you have some symmetries, the stress tensor contracted with the corresponding Killing vector. And in this case, it is very simple. So it's x. So let's say along the spatial line, so at t equal to 0. So this is all this is at x and x0 equal to 0, right? So this is along this integral is happening here, and this is the x coordinate, and this coordinate orthogonal to that is what I'm calling x0. So that is an integral which we take at x0 equal to 0. So this is an expression for the boost generator in terms of a local operator, so in terms of the stress tensor. And the notable thing is that we can express this density matrix in terms of a simple exponential of a local operator. Now, so some of the features we discussed here for Rindler space are actually very general features of quantum field theory when we take quantum field theory and we restrict observations to a finite region of space, or to a region of space, more than finite, I should say, a region of space which does not include the whole space. So if you have, let's say, space in quantum field theory, so these are spatial regions, and you have some region which could be finite or infinite, but does not include all of space, then you can always define a density matrix associated to that region, which is obtained by a calculation very similar to what we discussed there with the phi right and phi tilde, and that's one reason I discussed it in that way. And so we can define this density matrix, but in general it will not, and you can always take the log of this and write it as e to the 2 pi times some operator k, but in general this operator k will not be the integral of a local operator, something very special for the Rindler wedge that you can express it as the integral of a local operator. For general regions, it will be, this operator will be a mess, it will be very non-local and so on. This operator is sometimes called modular Hamiltonian. So it's simply the log of the corresponding density matrix. Okay, so that's just a definition. So here we should emphasize the fact that we started with the pure state, the vacuum, and by tracing over the left side, by restricting the observations only to the right side, we got a mixed state. We got this state with a finite temperature. That will happen in quantum field theory for any finite region. So for any region, so if it is a finite region or a semi-infinite region which does not include all of space, we'll always get a mixed state. Okay. Okay. And what that physically means is that, well, the vacuum in quantum field theory is a highly entangled state. I mean, the origin of the fact that it's a mixed state is because of entanglement. So there are degrees of freedom, local degrees of freedom of the quantum field theory that are entangled across this, between the left and the right. So we imagine that in quantum field theory, the fundamental degrees of freedom are localized at each space-time point. And the fact that we get this density matrix means that these degrees of freedom are entangled. Okay. So now I'd like to discuss. Are there any questions so far? Or?
Yes.
Yeah.
If you start with the thermal states, do the temperature simply add?
Yeah, good. So if we started with a thermal state, we'll get a mess. So we won't get something as simple as this.
Yes.
Yeah.
So in general,
No. So the answer is no, and we'll get something more messy.
Okay.
Right. Now, if you started with a thermal state and you went very close to the horizon, so the thing is, the original thermal state is you are referring to a thermal state where, with a temperature defined with respect to Minkowski space, right? A state which is uniform. So in that case, when you get very close to, if you were sitting at an R which is very close to the origin, you will be seeing a very high proper temperature if you're accelerating. And so locally there you can ignore that, that temperature. So locally very near the surface, you'll get results which are independent of the state you started from. So you could start from the thermal state, you could start from any pure state, and so on. And the properties very close to the horizon are going to be universal. Okay. But yeah, beyond that, cannot say more. Okay, so as a way to quantify this effect, or the mixed nature of this density, this density matrix, we can calculate the entropy associated to this density matrix, and we can do that for a general region. So we can assign an entropy SA to this density matrix, and we can do this for any region and any state of a quantum field theory, whether even if the initial state in the quantum field theory was thermal or not. For example, you asked me about a thermal state in the quantum field theory. There we started with a mixed state, and we can define a density matrix associated to a finite region or to the right Rindler wedge, and we'll get some density matrix, and we can calculate this entropy. So we can do that for any state. And people use this sometimes as tools for studying the quantum field theory or for studying the state to define these entropies. And as I said, these entropies are not very easily measurable, but people compute them as theoretical tools to study the quantum field theory. Okay, so let's discuss some of the features of this entropy. The first feature I would like to say is that these entropies are all infinite. Okay. So let's try to understand this infinity. So the infinity comes from the fact that when we get very close to the horizon, we have very high temperatures. Okay. So imagine that we have a massless field, and even if we had a massive field, when we get very close to r equal to 0, the proper temperature will be very large, and we will be able to ignore the mass anyway. And so we'll approximate this calculation as that of massless fields. And so we can say, well, we are integrating dr. And here we're going to make a slightly incorrect approximation, but it will be fine for making this point, which is to say that the entropy, we are going to integrate the local entropy at the local proper temperature, right? So we'll have the integral dr of the, also dx perpendicular if we have some transverse perpendicular directions, of some entropy density, which is the entropy density at the proper temperature T of R. So S of T of R. Okay. So if we do this calculation in d space-time dimensions, so entropy density. So this is there are d minus 1 coordinates here. So this will go like t to the power d minus 1, okay? And so this is going like dr, the integral of all the perpendicular directions will give us a factor of the area. And this will be some integral between 0 and infinity of 1 over r. I'm dropping all constants, of course, t minus d minus 1. I'm only focusing on the r dependence. And what we see here is that when r goes to 0, this blows up, right? This has a divergence at r equal to 0. So we can make the dependence on the UV cutoff more explicit by integrating only up to epsilon, in which case we get area divided by epsilon to the d minus 2, right? Just to make it more, so in 4 dimensions, we have area divided by epsilon squared. That's the divergence. That's this infinity we were talking about here. This divergence is completely universal. It is the same for any state, any reasonable state that we had in the quantum field theory. For example, you asked me about the thermal state. So for a thermal state, we'll have this divergence. For any other state, we'll have this divergence. And much of the recent progress in using entanglement entropy as a tool in quantum field theory has been to understand how to subtract this divergence and focus on the finite pieces that remain after subtracting this divergence. Or by defining, so there are some finite pieces remaining here, and much of the progress has been made by focusing on these finite pieces. I will not discuss that. So that mainly is for applications to quantum field theory. If you're interested, I could discuss those. Just to be a little more precise, I was slightly imprecise in this statement. In 4 dimensions, there are actually some logarithmic divergences, which are also universal, and then there is something finite. And sometimes people focused on this coefficient, sometimes one focuses on the finite pieces. Very good. Now, one way this entropy can be computed in quantum field theory, and that is normally this entropy is normally computed in this way, or at least as a cartoon. So we discussed there the computation of the density matrix. So if we are computing the density matrix, that was so we are evolving here in Euclidean time over a time which is e to the 2 pi times the boost generator. And in order to compute the entropy, what we need to do is to compute the trace of rho log rho, okay? And this can be done by evolving over some time beta, which is generic, and then take the derivative, of course, of the log of the partition function, and this then we set beta equal to 2 pi, and that gives us the temperature. Or sometimes what people discuss, for reasons I'll probably say later, they say, well, 2 pi n, and then you take the derivative with respect to n, and we take here as a continuous variable. Sorry, n equal to 1. Now the reason for doing this, for calling this n, is the fact that in general, so if we did this for a general region, we wouldn't have a boost, we wouldn't have a symmetry around this line. We still can go around by, we still go back to the same configuration after going around by 2 pi, or by going around by 2 pi n times. But not if not if we make n continuous. So I won't discuss this in whole detail, but there's something called the replica trick that allows us to compute this quantity by saying first we compute Cn for integer n, where what we do is we do a maybe I won't explain this. Yeah, I'll skip over this part. I'll stick it with beta. We'll come back to this later. Okay, so in this context, the divergence, that UV divergence we were talking about, comes from the tip, from the fact that when we make beta, which is not equal to 2 pi, so if beta is equal to 2 pi, then, and we take the trace of rho, so trace of rho, trace of rho would be given by just putting these two boundaries equal and then integrating, and we would get something. We would get the partition function. So we don't get 1 because when we define rho this way, it wasn't normalized properly. Okay, so we didn't really normalize it properly. So this is an unnormalized version of rho, and that's what we would get. But here what we are doing is we are, when we take beta different, we are really introducing a conical defect, a small conical defect angle. And so we'll have a singular point here, the origin, and that's why we're getting something infinite. Okay. Okay, so far, all the discussion so far up to now was in the context of quantum field theory. I now will discuss one feature that arises when we do the gravitational version, so when we include the effects of gravity. So there we were discussing Rindler space in quantum field theory. So imagine we had the same Rindler space, but now in gravity. We expect exactly the same, well, we expect basically the same temperature, okay? But now let's discuss the calculation of the entropy. And the calculation of the entropy has one new little twist that is very important. And it's the formula. It's essentially what I'm going to discuss is a version of the Hawking-Bekenstein entropy formula for gravity. And I'm going to try to discuss it in this language so that we see the big difference between computing this entropy in quantum field theory and computing the same entropy in gravity. Okay? So, as I said, the computation of the entropy in quantum field theory is associated to putting the quantum field theory in a space like this. From here, from the partition function on this type of space, we get S. Okay, by taking the derivative, by taking this derivative. Okay. Now, so I'm going now to discuss, so far everything that I said was quantum field theory, no gravity at all. Now we'll discuss gravity. Now, in gravity, if we wanted to compute this entropy, we are not allowed to put gravity on this space, because we're not allowed to put gravity on an arbitrary space. So the space on which we consider gravity has to be a solution of the equations of motion. Otherwise, it doesn't make sense. This is related to, I mean, this point I'm making is actually pretty important, and it's related to the fact that gravity does not have a stress tensor. If it had a local stress tensor, we would be able to put gravity on an arbitrary manifold, which we can't. And it's related to the fact that in general relativity we cannot define local notion of energy, local stress tensor. And it's also related to the fact that if you take a metric and you try to write down linearized graviton perturbations, and you try to write down an action which involves just a graviton and propagating on this arbitrary manifold that is gauge invariant and the linearized gauge transformations of gravity, then you find that the background should obey to lead in order the vacuum Einstein's equations with possibly, well, the traceless part of vacuum Einstein's equations. Okay, those was some random remarks. But anyway, so in gravity what we are allowed to do is to fix the boundary conditions far away. So we're not allowed to say that we have some manifold, but we're allowed to say that we have some manifold far away. Now, what is far away in this context? So far away in this context will be this region that is far in this region which had low temperatures. Okay, so we have something like, let's say, Rindler space, and we fix the boundary conditions far away in the region that is very cold for large R, and there we fix the value of the metric. And so we are imagining we have a metric which has the form, we started with a Euclidean metric which has the form d squared plus r squared dt squared. So the tau square is the Euclidean time, so it's the, let me see, we take t to it in that formula, and we get this metric. So that's the full metric, but what we are allowed to do is to say, well, let's fix some very large R, let's call it RC, okay? Large enough. And we are going to say that we have a metric at RC which has, let's say, this length, where the tau direction has length, in this case 2 pi. And now tau is the same as tau plus 2 pi. And now we'll attempt to change the temperature. Okay? And to change the temperature, the thing we can do is change the length of this Euclidean time. And we can do that by multiplying this metric by a factor of n squared. So that's the same as taking beta to beta, so 2 pi n. N here is not necessarily an integer. It's, let's say, close to 1. So that's the boundary, the new boundary condition we put here. And gravity selects how to fill this in. Okay? So we could fill this in the radial direction with any metric we want, but it has to be a solution of Einstein's equations everywhere. And the Einstein's equations really want to fill this in with a regular metric. And so that will involve taking a metric of this form, where we can pull out this factor of n squared, and we get simply a metric which is completely non-singular at the origin. So in order to contrast what we were doing in quantum field theory, we were taking the partition function of the theory on a space which was conical, and we had the freedom to choose the space of this way in the quantum field theory, because we can choose whatever space we want. While in gravity, the space gets filled as this disk here, which is completely non-singular. And then when we compute the partition function of gravity, so we can now go and compute the log of the partition function. In the gravity approximation will be simply given by the classical action minus the classical action. And this will be 1 over 16 pi g Newton integral square root of gr. Okay. So that's the naive classical action. But whenever we do this type of calculations, we have to make sure this action has second derivatives of the metric. But in order to have a well-defined boundary problem, we need to add the Gibbons-Hawking boundary term. So this is on the disk. this is on the boundary of the disk. Of course, this is all multiplied by all the transverse dimensions. The net result of this is, well, the transverse dimensions don't figure in this discussion and will just give us a factor of the area of the transverse dimensions, where now this integral is over the two-dimensional disk. And this is nothing else but the Euler character of the disk, which is just a factor of 4 pi. Okay. And then we get the formula area over 4 pi, or 4g Newton, which is the Hawking-Bekenstein formula for the entropy. Now this is the Gibbons-Hawking. This is just simply the Gibbons-Hawking calculation for black hole entropy, but described very close to the horizon, if you wish. Okay, where we abstract the essential feature that gives rise to the area formula. Okay. Yeah.
Usually, so we have solution GR.
Yeah.
The temperature is related to some scale.
Yes. Yes.
Can't we just vary the scale?
Mm-hmm.
Family
Yeah.
vary
Yeah.
the
Yeah.
mass?
Yeah. Exactly. You can absolutely do this, and that will give you this formula. That's what Gibbons and Hawking did. So let me just say what you're saying. So if we take the Euclidean Schwarzschild geometry, well, perhaps first I would perhaps recall some features of the Schwarzschild. So let me connect this. Before I answer your question, let me say a few words. So I described it in this way just to contrast the computation of entanglement entropy, which is infinite in quantum field theory, with the finiteness of the same quantity in gravity, and how the calculations are different, and why it is finite in gravity. Okay. Now, and I wanted to say that in this more general way, which doesn't necessarily refer back to black holes, but now, since you were asking me this question, let me discuss a bit this whole story in the context of black holes. Okay. So in the context of black holes, let me see where this was coming in our. Yeah, so that comes. I'll ask your question again in a few minutes. So if I haven't answered it. I would like to explain. I would like to clarify this a little more in the following way. So when we computed the entropy of these entropies in Rinder space, what were we doing? So we were taking when we were doing this in quantum field theory. What we were doing is we were taking that metric, right? The metric we see there for Rinder, and we were varying the temperature. Okay, so we were taking the metric fixed as given there and varying the temperature. So we started with the temperature that came from the original calculation 2 pi, and then we varied it slightly, right? That's what we did in quantum field theory. In gravity, we also attempted to change the temperature at that fixed cutoff position, and we did indeed change the temperature, but the space-time adjusted itself so that the proper temperature that someone... Yeah, I said this confusing way. Let me back up and say it again. So we took that Rinder space, which has a temperature which is 2 pi, which is given by the acceleration. Okay. So in quantum field theory, so let me say it more slowly. Quantum field theory, we had a temperature which is equal. This is the starting point, the starting state, and then we changed the temperature without changing the metric. We changed it to delta t, which is slightly bigger or smaller than the acceleration. Right. So we were considering quantum field theory in Rinder space with the temperature different than the acceleration. Okay. In gravity, on the other hand, we started with the same temperature, and is equal to the acceleration at this position. And then we changed it away from that value, but the space-time changed in the vicinity of the origin in such a way so that the temperature is again equal to the acceleration at the horizon. Right? So the metric of the space-time changed in such a way that the temperature became again equal to the acceleration at the horizon. All I'm saying is just simply the regularity of the Euclidean solution. So in Euclidean space, this was very trivial, so it was very simple to see. But I'm trying to repeat that same thing in the context of the Lorentzian signature. That is basically what is happening. The space changes itself so that the temperature near the horizon is always goes to the local acceleration. So somehow it's impossible to change the temperature of your spacetime of that Rindler space away from this value, right? I guess in the past people had said that nature abhors a vacuum, right? Nature doesn't like the vacuum. But here, so in this context, nature really likes the vacuum. So near gravity, gravitational systems, we really would like to go to this vacuum at the horizon. And that's the type of calculation that reproduces black hole entropy and so on. Okay. So now let's start discussing this in the context of black holes. Now, when we have a collapsing black hole, and I guess Sam Brownstein discussed this in great detail, we have a geometry roughly of this form. And this region of the geometry is close to the same region in Rindler space, right? So if we have full Rindler space, that region of the geometry is similar. And in fact, one can argue that if you start from any reasonable state here in the collapsing geometry, in the far future, the state around the future horizon will be the same as the state around the Rindler horizon, okay? And will have the thermal effect. And in this case, we had this Rindler Hamiltonian, H Rindler, or E Rindler. That Rindler Hamiltonian is the same as the Hamiltonian that moves us in time far away, as the ordinary energy Schwarzschild, right, of the black hole as seen from far away. In other words, if we write down the metric of a black hole as, let's say in 4 dimensions, just to make life easier. I think Sam discussed this in, sorry, not Rami Brownstein. Confused the name. So that's the metric of a Schwarzschild black hole in 4 dimensions. And the metric near R equal to R Schwarzschild has the form of, okay, so that's what's the collapsing black hole. Then there is the eternal black hole, which is what I really was, whose metric I'm really writing there, the exterior region, so this whole region. And the region near the horizon, so here and all around here, is given by Rindler space again. So if we expand around R equal to R Schwarzschild, we can see that this space has exactly, up to a very simple change of coordinates, exactly the Rindler form that we discussed before. And maybe I should call this time tilde. So this is the Schwarzschild time. And what you find is that this Schwarzschild time is related by a factor of beta of the, so this factor is beta over 2 pi times the time, Rindler time that I defined over there, right? Where beta is the temperature of this black hole, which is inversely proportional to R Schwarzschild. Okay. So exercise. Maybe Rami already gave you this exercise. So to compute, expand around R Schwarzschild and figure out the precise change of coordinates to go to Rindler. And in the process, you will have computed the black hole temperature by demanding that this circle, so you go to Euclidean space, so you put a plus there. You demand that tau tilde has period tau tilde plus beta. And then you calculate beta as a function of R Schwarzschild. You'll get some constant. You calculate this constant times R Schwarzschild. You can calculate this constant and you'll find the precise change of coordinates. And the conclusion of that will be that the precise numerical relation between the Schwarzschild Hamiltonian, which is, or the Schwarzschild notion of energy, which corresponds to, is conjugate to translations in this time t tilde, to Rindler energy in this near horizon region. Okay. Okay, so that's what we have, and So then this Rindler effect, this thermal nature of the vacuum in Rindler coordinates becomes the source of Hawking radiation. Or in other words, so in the case of Rindler space, it was totally artificial to restrict to the right Rindler wedge. It was somewhat artificial. Well, it was natural for the accelerating observers, but that seemed a little bit artificial. But on the other hand, in the black hole context, this wedge is the wedge that can be accessed by measurements that we do here at null infinity. So since that's the wedge that can be accessed by this type of measurements, it's natural to restrict attention to that wedge. And when we do that, we find that even if there was a globally well-defined state, the state of this system will look mixed and will look thermal with a thermal density matrix given by e to the minus tilde Schwarzschild divided by the T Schwarzschild. So this, let me call this beta tilde, right? Beta tilde is the Schwarzschild energy temperature. So the same discussion, the same argument that we made, the same argument about the same argument that we did for Rindler space, saying that the density matrix for any quantum field theory is given by the action of the boost Hamiltonian. The same feature is true for the Schwarzschild geometry, which has a symmetry of boosts around this point. Okay, and then the density matrix is again exactly it can be expressed for a quantum field theory on this background can be expressed in this form. Okay, so this is the density matrix for in quantum field theory on black hole background. Okay. So for so in the context of quantum field theory in the black hole background, the entropy then would be infinite. If we were doing so, let's say in this type of configuration, the entropy of that density matrix in quantum field theory would be infinite and be proportional to the area over epsilon squared in 4 dimensions. On the other hand, in gravity, if we did the calculation of the entropy of gravity, then so the traditional way of presenting the Gibbons-Hawking calculation is to say that we take Euclidean time and this black hole metric, and we find that then this is a circle at infinity. We have a circle size, which is given by this beta tilde. And this circle shrinks smoothly at the horizon. And that's what, so we adjust beta tilde in such a way that the circle shrinks smoothly. Okay, so that will give us this relationship between beta tilde and RS. And then we calculate the action of this whole thing. It will be the action, well, will be some function of RS, or we express it in terms of beta tilde. And then we take the derivative that I erased, but the general formula for calculating the entropy given the partition function. And to do that, we get the area formula. Okay. So if we say it this way, it's a little unclear why we get the area. And as they even said in the original paper, we get the area because the rest, the rest of the geometry is completely, it has an action which is proportional to the length of the circle, so will not contribute to the entropy. But this little piece of the action here at the end has a piece which is independent of the temperature, as you can see here. It's just a constant. And so when inserted in the formula for the partition function, which has given us this entropy. Yeah. You were saying something? Okay. What time did I start?
I started at 4:30.
4:30. Yeah. Go. Okay. Now, okay, yeah, so the entropy in gravity, on the other hand, is area divided by 4g Newton, which is finite. Okay. And as you probably know, one is tempted to, well, we think that the black hole as seen from the outside really has a finite number of degrees of freedom, which are counted by this entropy. Okay. Now, when we calculate this entropy in quantum field theory, it is fairly clear what we are counting, right? We are having these fields outside the horizon, which are all in a thermal state. They're all moving up and down because of this temperature, and we're just computing that entropy. It comes from all the random configurations of the fields outside. That's where this entropy is coming from. This entropy, on the other hand, this argument that we are given here, or the Gibbons-Hawking, explain clearly why it is finite, but it doesn't give us a clear picture of why what we are counting. Okay, and so that's in string theory we have many examples where we can independently calculate the entropy and we get results which are consistent with this formula, but we don't have a really crystal clear understanding of why we are getting this formula which is proportional to the area. So how do you understand this counting directly from the gravity point of view? How do we give an explicit description of the Hilbert space of these black holes within the gravity approximation? Sometimes we can use this dual description via ADS-CFT that I'll perhaps review later, where we can actually give a description of the microstates. But so far, let me not assume that, and let me just state this as a question. Now, one can be here very skeptical and say, well, you know, you got all these formulas and so on, that's all fine, but I look at this geometry here, and, you know, this geometry has this asymptotic region in the future, and this other asymptotic region in the future. And so it has two asymptotic regions. And yeah, so sometimes things can come in, something is lost into the interior. And so, okay, so you got a mixed state because you lost some of the information into the interior. So it's not mysterious at all, and if you weren't to include everything, then you will find something unitary, but otherwise you won't. Okay. Yeah. Now, one indirect evidence, but fairly solid, that the black hole should be viewed as a unitary system from the outside, so that if we remain outside the black hole, that we should be able to describe the black hole from the exterior as a unitary system, comes from the second law of black hole thermodynamics. I mean, in other words, so if we had that the entropy should always increase, okay, well, the entropy, I mean, you can throw entropy inside the black hole, and well, in this whole surface, the entropy increases. But naively, you have that the entropy from this point of view decreased because some of it went inside. Of course, the whole work of Bekenstein and so on was based on thinking that the second law of thermodynamics should work as seen from the outside, right? And the second law should work if we think about the total entropy as seen from the outside as equal to the area over 4g Newton plus the entropy of ordinary entropy outside. Okay. So we're perhaps going to explain a little more clearly what should be this ordinary entropy outside. So certainly if we had, let's say, a gas, some gas outside, which has some entropy, and we're throwing that into the black hole, it certainly should include the entropy of that gas, right? But you can also ask whether we should include the entropy of these fields that we computed here, right? So if we ignore the effects of quantum mechanics, we can ignore this entropy. Recall that this whole Unruh discussion that we were having here was a quantum mechanical issue. So if we only include sort of kind of classical entropy, okay, so we can have some classical entropy of a gas outside, and then we include just only that. But we also have this when we want to make sense of this in the semi-classical theory, where we have the classical answer plus the order 1 answer we get in quantum mechanics. So in principle, we are supposed to add that infinite piece. So we get here another piece which goes like area over epsilon, right? So all this includes the so-called entanglement entropy outside. So a more precise way to define this is that this should include the so-called entanglement entropy outside, or more precisely is the entropy outside. The same thing as I defined before, but now a little more precisely defined as being that the trace of, first we form the density matrix outside the black hole region in the quantum field theory. So this is a quantum field theory computation. And we compute the entropy that we were defining in the beginning of the lecture. And it will be divergent, okay? But these divergence is, but if we did a full one-loop computation, we would also get divergence, divergent contribution to the Newton constant, and which we will have to cancel with a counter term, okay? So actually we get another contribution at one loop, which will come from the divergent contribution to the Newton constant, and these two pieces then cancel and leave some finite piece here, right? And that would be the quantum corrected black hole entropy. So somehow there is this this infinity. We shouldn't be too scared about it. It's cancelled by similar infinities that appear in the Newton. I'm oversimplifying here slightly, but let me just say it this way. So conceptually, this is the way this infinity is removed, and we get some finite piece outside. Okay. Now, it turns out that this the idea that the second law of thermodynamics should hold outside the black hole implies a certain property of quantum field theory, which is the following: that if you take the same Rindler space we were considering, we can consider various states of this quantum field theory in Rindler space. We could consider the vacuum, which is what we've been mainly discussing, or we could consider some other state, like the thermal state you mentioned, or a state which contains some stuff that is falling into the black hole and so on, into the horizon. This is in quantum field theory, no black hole here. Quantum field theory in Rindler space. So we could have, when we reduce the system to the right Rindler wedge, we could have a density matrix of the state we're interested in, or the density matrix of the vacuum, which is what we've been discussing so far. So for this we have a simple expression. This one will depend on the state we have. And it turns out that if we compute the difference in entropy between any state and the vacuum, so this is the entropy associated to rho minus the entropy associated to rho vacuum, this should be less or equal than 2 pi times the difference in boost energies between the state we are interested in and the vacuum one. Boost energy, or equivalently Rindler energy. So if we take the Rindler energy of the state we are interested in, its expectation value minus the expectation value of the vacuum. I mean, we can define this to be 0, and that sets a 0 of energy. Then we just have the Rindler energy. So that this inequality should hold. I didn't discuss this. I ran out of time, but I'll discuss it next time. This is the so-called Bekenstein-Cassini bound. Bekenstein had a bound which looked kind of like this, but this is the more precise version that Cassini formulated and then proved. And we'll discuss why it should be the case, and first of all, why we should have this because of black hole thermodynamics. Why we should have that if the second law holds. And also we'll argue that this is a generic property of quantum field theory in Rindler space. Okay. Thank you. Yeah.
So you mentioned that we could extract a meaningful part of the entropy. Can we see this as a renormalized version of the entropy by adding counter terms to some action?
Not that I know of, and I think not. But the reason is that entropy is not. Yeah, your intuition would be correct if we were computing ordinary observables. So the entropy, as we were defining it, is related to an observable which would be a codimension 2 brane, because when we compute the entropy, recall that we were doing this trick with the cone and so on, right? So we had this point which has codimension 2 in the full spacetime, is extended in the other directions, but is localized in 2 of the transverse dimensions. And if we had a brane that had the codimension 2, then we can extract finite pieces by subtracting this directly these counter terms. Because it's not quite an observable in the same sense, I suspect. Well, maybe still for the counter terms it might work. I'm not sure. Let me see.
There is still an unambiguous meaning that we can give to these finite terms.
Yes. If
you're
you're
to regularize this,
yes,
I would
yes,
expect some
yes.
different finite terms.
Yeah, that's right. So, well, I'll discuss how to. Well, maybe I'll. So there are various ways to define finite things that are unambiguous. So one way is what we were doing here. So even though this might have some ambiguities and this might have some ambiguities, this difference has no ambiguities. And the reason is that these divergences that we had were universal. So we'll have the same divergence. As long as we regularize these two calculations in the same way, we'll get the same finite answer. This is a zeroth order explanation. If you dig a little deeper, there could be some ambiguities in this quantity in some special theories, like free scalar fields and so on. But then they translate into ambiguities you have in defining this energy, so this inequality still is true.
Because the energy is
So
always ambiguous.
well, so there is a finite shift, and that's why we took this difference. So here also it doesn't matter. So this shift doesn't matter. So these ambiguities I'm discussing is, for example, for a scalar field, you can define a stress tensor, which is the ordinary stress tensor, or you can add pieces which are related to. You can add total derivatives. Terms like this, right? So for example, the difference between a minimally coupled and conformally coupled scalar field are terms of this form. And in such situations, these differences could depend on the expectation value of phi squared at the horizon, this side. Could have an ambiguities which are related to what terms you add here. And then similarly, these energies could have pieces which are ambiguous, which depend on the value of phi squared at the horizon. But these are minor details. To first order, what you should think is that these are well defined. Then if you dig a little deeper, there are little details. But the zeroth order thing you should understand is that they are well defined. Another thing people do in other applications is to for example, let's say in 2 + 1 dimensions, you can define the entropy for a circle of radius r. And in that case, the entropy has a piece which goes like r/epsilon plus perhaps this finite piece, right? And so in this case, what is done is to calculate the quantity 1 minus r dr, right, of this S of r. And then you are exploiting the fact that the divergent pieces will be linear in R. And then the finite piece might have some R dependence, but will be finite and will not cancel. So for example, if the finite piece is independent of R, it will survive this operation. And the linear piece will not survive this operation. So that's one other way of making it finite. So in general, the tricks are to calculate quantities in which this divergence is cancelled. And this is how we deal always with divergences in quantum field theory. So almost anything we calculate in quantum field theory is going to be divergent. And we normally extract these divergences by taking ratios or comparing between two states, and then the divergences go away. It's physically meaningful calculation. And so much of the recent progress has been in understanding better the quantities which are finite.
When calculating the gravitational entropy,
Yeah.
we use classical GR or
Yes.
So this theory naturally cuts off at the Planck length. So that seems like the reason why we got a find answer because we have a natural cutoff.
Yeah.
Is there really a difference between the CFT entropy and the gravitational one?
Yeah, so there is difference. So the gravitational entropy is one contribution, is the leading contribution, and the field theory entropy is a correction to it. Okay, so if you want to compute the entropy of an actual black hole, you would get the wrong answer if you only include this piece. So to get the correct answer, you should take this piece and sum whatever you get from this piece. Of course, it's not this, it's the finite piece which is important. Right? So the full answer is this piece plus area over epsilon squared plus finite, right? And then you should do quantum calculations properly, so you should include the counter terms and so on. You include the counter terms, you get area over epsilon squared. The counter term is local and only cancels this piece, but leaves the finite piece. So the finite piece gives an additional contribution to the entropy. And this type of additional contributions have been computed for extremal black holes by Sen, for example, and other people. And they've been shown to match with some predictions that are more indirectly obtained from string theory. That maybe I'll summarize next time those other indirect calculations.